Go for it. All right, welcome to I think, the most anticipated meetup of 2015 so far for LVTech. So we have Brian with us. He's going to talk a little bit about robots. We are live streaming this, so hopefully it's working. We've been getting better. We've been getting better every month or so. So we've only been doing, 2 months now with the live stream? So if you're watching at home, hope it works. If not, you should have come here. You would have got some pizza. And how many of this is your first time to an LVTech event? Wow, a bunch of you. Well, good. Welcome. Glad you could come. We don't normally have it at this event. This could be why the regulars aren't here, because they're at Ben Franklin going, where is this meetup? Hopefully not, but we do a meetup every month. This is a tech talk, so it's going to be just one presenter going into a technical topic like robotics, as you can see. Next month, we're doing 3 presenters. There's going to be one presenter talking about a new mobile app they're building, one presenter talking about a food-related startup applying technology to solve some problems that restaurants have, and then a Kickstarter success, a guy who built, or not really built, but manufactured a lot of NFC tags and his use cases for that, which is pretty interesting. That'll all be next month. That's one of what we call our traditional meetup or something like that has 3 presenters. And then the month after, we do a spotlight meetup where we're going to have a set of people who have either worked in the crowdfunding space or have successfully crowdfunded something, either on Kickstarter, Indiegogo, Rocket Hub, something like that. And we'll ask them questions, get a little information about what it's like either to run a crowdfunding or there's 2 startups that we'll have there that are involved in the crowdfunding space, advising people or actually building a crowdfunding platform. So explore some of those things. We will have an open mic at the end of the night, so if you have some technology or entrepreneurship or some type of tech-related thing going on, we'll open up the mic for you to tell everybody about that. And also want to say, if you didn't get a chance to take a tour of the FabLab before this started, it will still be open at the end of the meetup. So you can head back down there. It's the 3rd floor. Take a tour of all the cool stuff they have there. Make sure you see it all. Make sure you see that they've got a full wood shop. They've got a laser cutter engraver. They've got a couple 3D printers, computer labs, some electronics stuff, a Tormac CNC machine squirreled away in the back someplace, a recording studio, a bunch of fun stuff. And grab one of the people that look like they know what they're doing and ask them, like this gentleman right here. Grab James and... There you go. So tour of the tech lab, because, the people are in there tonight. So grab him, ask him lots of questions, and see how you can utilize some of the cool stuff they have down there. And after you see some of the cool stuff you can build with robotics, the FabLab is running a bunch of robot courses. There's a more traditional schedule, which is, was it Tuesday, Wednesday, something like that?
Yeah, it would be meeting once a week.
Once a week?
And then we have a couple weekend workshops.
Right.
An all-day Saturday event.
And then, some weekend classes that are just one weekend, and you build a robot, have a lot of fun. So definitely, if you find this interesting, sign up for those courses. They need people to be involved to run them and make them successful. See the green books right there? I think there's some in the back, and there's some down the FabLab.
And we start on page
438. 38. No 4. Drop the 4 completely from that. 38 for the courses that FabLab offers. And with that, I'm going to turn it over to Brian, and I'll be back at the end of the evening.
All right. Thank you very much, Tim. Thank you all for coming tonight to learn about robotics. For those of you who don't know me, my name is Brian Feldman, and I am heavily involved in robotics and robotics consulting. So tonight we're going to talk about what robotics actually is, how I got started, an overview of the Arduino robotics platform, and how you can get involved in robotics if you so desire. So everyone a lot of times thinks of robotics as, big arms in factories and crazy stuff moving around. But I like to think of robotics more as anything involving programming and interfacing with physical devices. So not only moving things around, but also sensing things as well. So on the screen here, for example, on the far left, that's actually a water flow sensor. In the middle, you have ultrasonic sensors. Yeah, that might help. Thanks. No, you got a lot of those from the harp, right? Yep. All right. This is actually a servo for moving things around, and this is a stepper motor right here. So you could do input in a variety of ways, sensors, keypads, buttons, getting data off the internet, and you can also output data in a variety of ways, screens, motors, servos, and I've actually used thermoelectric modules in some projects to keep water hot or cold. So some applications, we always think of the robots in the auto factory putting together cars. You're doing the same thing over and over again. It's something that's very straightforward to program because there's not a whole lot of change involved, from one car to the next. And you want very good consistency when you're in a manufacturing environment. To something like the Asimo, where you got a little bit of artificial intelligence, some balance, a lot of different features and functions that need to be programmed in there, a little more complicated, responding to things on the fly. All the way down to smaller projects, such as this ultrasonic sensor that I designed to run low power on a set of batteries for a couple of years, and I actually have that sitting right up on the table. I can demonstrate that later this evening for you. So here's an application of robotics that probably you should not duplicate, but the traditional arm that people like to use, and this is on YouTube. Sorry about the quality, but you have amusement park rides like this, so I don't think these are the first people that have ever done it. But even though it looks bad, I want to say there's probably 3 things that they're doing right here in spite of the fact that everything else is wrong. The first thing I want to say is if you look very closely, the guy is harnessed into the seat very, very well. The second is you see a white line there, people drew out there. It is at the very extent of the reach of the arm, so people know if they're outside the danger zone that they'll be okay. And third, the guy is doing this in a supervised environment, so if he injures himself, there are plenty of other people around to call for help. Other than that, don't do this. Another application of robotics that many people might not think about, but in your car. If people have driven cars before, I don't know, about the year 2000, you might have had a completely mechanical throttle control in your car, which basically is your foot on the gas pedal, and it's a direct mechanical linkage to the throttle body through a cable. Later cars, anything built today pretty much has a drive-by-wire throttle control where your foot's not directly connected to the throttle, but you have a pedal position sensor connected to the engine control module, and the throttle body is actually actuated with a servo. And this is one of the things that we've seen. Toyota's famous for getting in trouble for it because they were saying that people weren't pushing down the accelerator, but the computer was commanding the throttle body to be fully wide open. But there are some advantages to the drive-by-wire throttle control, one of which is it eliminates a lot of components for doing things like cruise control because, for example, you don't want your foot on the accelerator if you're using cruise control because you want the computer keeping the speed of that. Prior to that, in the mechanical system, that was generally done with a vacuum-actuated servo, which was prone to leaks and problems over time, which you would eliminate with this. And also for emissions control, you can change the opening and closing of the throttle body to change the way the engine's operating and make the operation a lot smoother. In case someone, for example, would stab the gas pedal, you can open up the throttle very gently instead of all at once and cause the engine to bog down or something goofy to happen. Another interesting thing about robotics is the areas that you need to be an expert in. In traditional programming, you generally need to be an expert in computer software. And there are people that are great with this. Some people love programming 16 hours a day, getting very, very deep into it, doing one thing, and doing it very, very well. And I salute those people. If you're into robotics, if you're the type of person that's maybe a jack of all trades, you do a little bit of each thing, a little bit of computer software, mechanical engineering, electrical engineering, microprocessors, and ethnography. Does anyone want to take a guess at what ethnography is? Okay. No? Ethnography is the study of people and how people do things and how people use things. And that's very important when you're designing anything, even when you're designing traditional computer software. You want to make sure it's something that people can intuitively understand and use, and it's not too difficult. And the great thing about robotics is that you don't have to have a PhD in each one of these areas to be good. You just have to know the basics, enough to get by or to know what you need to look up to actually get something done. So in traditional programming, a lot of times the areas of importance you'll see, power, how many gigahertz does the processor have, raw speed, security, redundancy, data encryption, and the user interface. With robotics, you have a whole other dimension because you're dealing with physical devices. So you might be operating in a strange environment that's very dusty, very hot, very cold, a lot of vibrations, or if you're under the hood of a car, all of the above, getting mud thrown at it. There's safety involved, as we saw in the video. Power consumption, if you're out in the middle of nowhere, maybe you want sensors to run for a couple of years without having to change the batteries, whereas a lot of times if you're doing traditional programming, you're plugged into the wall and you can suck down as much power as you want. You're using physical devices, so cost becomes important, even though cost can be important in traditional programming too with the different types of hardware. And a lot of times diagnostics are important too because you have so many things interfacing with each other. We're all familiar with the check engine light on our car. The car is trying to figure out, if something's not quite right, what exactly is going on, what should I check first so I can follow a troubleshooting tree and get things operating properly again. There's so many different things to check. So a little bit about myself, how I got started in robotics. I had a programming background back in high school, and like a lot of people, I wanted to design cars. Anyone else in the audience wanted to design cars when they were back in the day? One? That's all? Okay. All right. Two? So I had the programming background. I went to Penn State and got a degree in mechanical engineering. Penn Staters? No one wants to admit to it? Okay. Several jobs. What? No, okay. Then I went to Carnegie Mellon for a master's degree in engineering and technology innovation management, which is sort of halfway between an MBA and an advanced engineering degree. And I finished that up right at the end of 2008 as the economy was falling apart, so I started consulting. And the way I got into robotics was I started redesigning an ampule sealer for a client who knew me very well. They actually wanted someone who was well-versed in instrument design, and if they hadn't known me and I had said, hey, I know robotics, they would have said, well, why do we want you? We don't care. We don't need a roboticist. But luckily, they knew me and it worked out very well. And then a couple of years later, I got a call from a guy in Boston who told me that, it was very difficult to find someone who dealt with robotics. And it was an 11th hour last-ditch effort to find me. And I'm thinking, if I'm the closest guy you can find, and this guy's 20 miles from MIT, then maybe there's a need that needs to be filled here. One other interesting thing about Carnegie Mellon, have any of you seen the movie Bullitt with Steve McQueen? The famous car chase scene where he's driving the green Mustang through San Francisco. Well, Steve McQueen went to Carnegie Mellon, but unfortunately he did not graduate. He was expelled for riding his bike through the Fine Arts Building. And that's one thing they don't tell you on the tour. But now you know. So some interesting projects I've encountered, the ampule filler and sealer. I'll show you respirometer, SCADA system sensors, center pivot irrigation system. Have any of you flown across the country and seen this from the airplane? See all these green circles? Well, the land is not naturally like that. What they're doing is you have a device like this, just generally about a quarter-mile long, and it's fixed at one point that has a well pulling up water. And that thing swings in a huge circle, which creates these green circles where there's actually water and the land is irrigated, and then you have the dry zones outside of it. So I got a call from a guy who wants, control system for that. And I was actually down there in Oklahoma a couple of weeks ago and got to take a ride on a center pivot, which I don't think many people have done. Got a call from a guy who wanted a hand washing detection system, chemical tank level sensors, electronic braking system for inline skates, internet-connected air quality sensors. Someone wanted a car seat to detect if someone was leaving a baby in there and the car was getting hot, like they forgot their kid. Evidently that happens. The most interesting guy I talked to called me up and he's like, hey man. And evidently he's in Northern California. I'm thinking, oh my gosh, I know where this is going. It sounds like I'm talking to Cheech and Chong. But he wanted a control system for a pot growing rack. I haven't heard from him in a few months, so I don't know what he's doing. Possibly. Well, you could smuggle a cell phone in and still call me. At least let me know what's going on. A strobe lighting system, a wireless scrolling letter lighting system, redesigning medical equipment, and an aircraft sensor display on an instrument panel, just to name a few. This is the respirometer I promised to tell you about. This is basically testing the limits of what the Arduino Mega Board can do, but what a respirometer does is it's a device where you can take a biological sample of dirt or soil, and you want to know how much oxygen the sample is using, so you know what's in it and how healthy it is. So first thing you need to do is you have an electrolysis cell which generates a set amount of oxygen, and you need to run a certain amount of current through it and measure the amount of current. It'll generate oxygen to fill up what the soil sample is depleted. So the electrolysis cells would go here. These are the 3 thermoelectric modules that I promised you I'd use, because you need to keep the 5-gallon water bath, which is in here, at a set temperature so that you can replicate the experiment. In addition to that, it would be over here if I had the picture, but you need magnet spinning motors to stir the samples, which would be in here. And you also need to control a water pump, which is in there, and monitor temperature sensors on the thermoelectric modules to make sure that you're not overheating anything. Temperature sensors in the water bath. And to top that all off, you want to post that data to a PC so you have the data collected and stored in a database. So this is a close-up of the board that was developed for that. You see, basic components, MOSFETs on their connectors, a big capacitor, multiplexer, that's a barometric pressure and temperature sensor. And there's another temperature sensor. So a lot of stuff going on there. And I used an ATX power supply to power that, because we needed 60 amps on 112-volt rail, and found a power supply that produced that. Here's a video of the ampule sealer and filler. I'll just show it to you because it's much easier than actually explaining what it is. So these are ampules here. They're almost like test tubes, but they have very thin glass up at the top, and in a minute or two I'll show you what will happen is there'll be a flame coming out of here, and those ampules the glass will melt and form a hermetic seal. This is the liquid filler and gas injection portion of the unit. So here's the liquid filler, and if it detects an ampule, it's going to push up the liquid filler and inject liquid into the ampules right before they get flame sealed. And let's see, what's next here? Yeah, here's the flame. So they're forming a hermetic seal. If you notice, there's switches right here that detect if these guys have actually gotten onto an ampule, so that you don't go injecting liquid where there's no ampule. And this is the base unit here, the one with the carousel rack and all the ampules. That has an Arduino board in it. This device here is used for purging gas, the one that goes up and down. The liquid filler's over here. The gas purge and liquid filler are getting Arduino boards in them as we speak. They're being redesigned for that. But they're designed so that you can run either just the base unit here, and then you could buy the add-on modules separately if you like. See, there are cables going through them. And this is the whole thing in operation all at once. But the base unit is running on an Arduino using very minor amount of the capabilities that the Arduino actually has. And then there's my hand. Oh. Okay, and another thing that I've been working on with Mr. Derek Storm in the back here is inside this building. And you might think that that's a tomb for someone who's very, very important, that someone very important died and built that for themselves. Except for if you look real closely, it says Bethlehem Municipal Water Authority there. So no one actually died and went in there. It's a facility where they're shuttling around water into different lines. And inside they have a PLC system to monitor the pressure and flow of their different lines. Some of their sensors are right here. So what we did was we built a board running on an Arduino Mini, which is right here, to monitor the current, because we want to compare what we can get for monitoring current with this little board here versus what they're getting with an expensive PLC system. And I have parts of that setup replicated up here. This is going over Ethernet to a cradle point device, and a cradle point's a wireless device that you run on a cellular connection through AT&T or Verizon, for example, and then you can post data directly to the internet from wherever you are. And you post the data to the internet, you get data like this out of a database. You get all your parameters here, and all your readings, the voltage of the system. This is on AC power, so I just forced it to -1, and then the address of the device it came from. But you can see, for example, current sensor 11 sensing 14.24 milliamps. And it looks a little better if you have an interface like this, so that you can see over time, what's happening, going on. You have a history, and it'll send out alerts if you need to, and make the appropriate reports that you'd like. So the question is, why now? Why is now a good time for robotics? Why are we not talking about this 5 years ago or 10 years ago? And the reasons I came up with for why now is that the Arduino has become much more popular in the past couple of years because it's something that's very, very low cost. It's open source, and there's a lot of community support. The microprocessors that they've been using, the technology's been around for years, but a lot of times, it was expensive to use in the past. The market was fragmented. Things were closed off, so you couldn't tell exactly what was going on. And it was very hard to find people who were actually using it, so there wasn't the support. You couldn't go ask a question as easily as you can with the Arduino. And you combine that with the maker movement, 3D printing, and everyone wanting to build things. The robotics falls right in with that. And it's a rapidly developing field that can fill many unfilled needs based on some of the interesting calls that I get for projects. There's a lot of stuff that you can do now that wouldn't have made sense to do before because you're able to do things at a smaller scale and much lower price. So a little bit about the Arduino. Has anyone here ever heard of or used the Arduino? Okay, good. Some of the things that make it nice are, one, it's open source hardware. So you can buy the stuff already pre-built, which a lot of times makes sense, but the schematics right there is provided by the manufacturer if you wanted to build it yourself or if you're worried about the people who are making it going out of business. The IDE is open source and it's available on most operating systems. It's very simple to install. The programs, which are called sketches, are developed in C++, and a lot of people are familiar with C++, JavaScript, and related languages, so it's a natural transition for them. It's a straight USB connection of most of these boards, so you can be up and running in 10 minutes, and just about every machine has USB these days. There's some way to get USB. And another nice thing, being open source, is there are many different but compatible form factors available depending on the features you want. So if you want something that's big and has a lot of inputs and outputs, you can get that. If you want something that's small and low power, you can get that as well. If you want something that has wireless built into it or Ethernet built into it, there are also boards that have that specifically to reduce the amount of effort it takes you to develop what you want. So some of the most common Arduino boards, the most common one's probably the Uno, and that's about the size of a credit card there. And the specs here, they look very, very small compared to what you're used to in a desktop computer. It only has 32K of flash memory, 2 kilobytes of RAM, and it's running at 16 megahertz on this processor. And I liken that to this is about what they were using to send man to the moon back in 1969. So you can get the same amount of power here. The difference is this is a removable integrated circuit chip. That's the actual ATmega 328, and you can buy these for about $2.50 in volume, $2.50. They also have the surface mount die version here, and they make Unos with the surface mount die version. This is about the size of 2 postage stamps, and I have one of those right up here. That's all the bigger it is. But if you need more power, more inputs and outputs, more memory, you can go with a Mega. It costs a little bit more, it takes a little bit more power, but the opportunity's there. You see it has a lot more pinouts, and sometimes that's necessary. So here's a close-up of the Uno. What it can do is you can do digital inputs and outputs. So any one of these pins here, 0 through 13 and analog 0 through 5, can tell you whether it's higher, any value coming in is high or low. You can do analog input on an analog pin. So if you have a voltage between 0 and 5 volts, it can tell you what voltage that is. It can do serial communication just like a modem with some libraries. So you can communicate with a whole bunch of different things, Ethernet boards, wireless boards, other Arduinos. Any of these pinouts with a little tilde in front of them, 11, 10, 9, 6, 5, and 3, you can do PWM output, and I'll explain that in a little more detail later. And along with PWM, you can do servo control output too to control servos. there's a timer in the microprocessor, a couple of timers actually that control all the functions, making sure that the pulses happen at the right times and the serial communication happens at the right times, giving you that functionality. So it can do a lot of things, but it's really up to you to make it happen. The Arduino community also has a lot of shields available to make it easier to develop. And what a shield is, it's a board that matches up pin for pin with the Uno, and you can just slap it on and sandwich it on without doing any other wiring or connection whatsoever. And most of the time they have the drivers with them so that they're very easy to use. You don't need to write a whole bunch of code by yourself or deal with the very intricate communications of each of these pins to make things work. And the nice thing is, once you stack a shield on, you still got all the pins out there, so if you need to put other things on, it'll just pass right through to the baseboard. And you can also build your own shields, either with a prototyping board if you like to do soldering, or if you have to do a production run of 10 or 20 shields, you can develop a PCB in free software, and either you can probably make it at the FabLab here in a CNC machine, or you can send it out to a place like PCB Express and pay your money, and they'll mail it to you in a week. Other components you can interface with anything you want to. If it's electronic, you don't have to buy special Arduino stuff or anything like that. But you can interface with relays, MOSFETs, solenoids, and the same sensors we saw on the third or fourth page. Water flow sensor, ultrasonic sensors, that's infrared, servo, stepper motor, and the temperature and relative humidity sensor. So, as I said before, most of the shields, and actually a lot of components, have drivers available which allow you to just use basic functions that the manufacturer or someone in the open source community has already made to make it very, very easy to get what you want out of the units instead of having to delve into the details. And the nice thing is most of the component data sheets actually have the interface specifications on them. And just about everything will use either serial, PWM, servo PWM, pulse length, a pulse count, for example, if it's measuring a flow, or like a Hall effect sensor for a wheel spinning rotation, resistance, an analog output, or a digital input or output. Like, for example, a button that's on or off will give you a digital I/O. One of my favorite sensors here, this particular ultrasonic sensor comes from Robotics, and it's actually the same sensor that I have in here encased in epoxy. One of the neat things about this one is there are actually 3 ways to get data from this sensor. It'll give you an analog output, pulse width, or actual serial communication. So here's an example of what the data sheet would tell you about the sensor. It says you got to provide power in, VCC. You'll hold pin 4 high to start sensing. Pin 3 will give you an output. It'll give you a voltage. It'll level off at some point, say maybe 3 volts, and that'll correspond to some sort of a distance. Or if you read pin 2, you'll get an echo, and it'll give you a length here, and the time that this guy is high corresponds to the distance between your sensor and what it's sensing. Or if you wait till it starts sending serial data, it'll send your data in serial format so you can read that as well. Because sometimes, for example, you don't have any analog voltage and analog in pins left over, so you don't want to use the analog in, and maybe it's easier to use the pulse length. And sometimes you want to use the serial, if you have extra resources, or you want to make sure that you're, 100% accurate. Because sometimes you can get a little bit of variation in the other two, depending on the timers or the voltages. Another very interesting sensor, definitely not developed just for the Arduino, but it's called E-tape, and it measures the level of any fluid that you immerse it in. We actually got some of it right here. This is E-tape. So this particular one is 12 inches long, but they can print it in any length they want. This is actually 3D printed. And so the question is, well, how does this work? All right, the E-tape has 2 resistance elements in it. It has a reference element in it because resistors can change their resistance depending on temperature, and you could be using this in a wide variety of temperatures. And then it has a sensor element, which is a resistance that changes with the fluid level. And this here is the thing they provide you on the data sheet that says if you sense the resistance, for example, as 1.5 kiloohms, well, that corresponds to a liquid level of 5 inches. So you just dip this in water, measure the resistance, and you can back calculate how deep the water is. And here's an example of a schematic that you might use when you're building electronics for it. So this is a very simple voltage divider. There are many ways to do this. You can use op amps, you can use Wheatstone bridges, but this is one of the simplest things you can do. And then that relates to this equation here. You just use you know what your reference resistance is, you know what your Vin is, you measure V measured, and based on that you can calculate what the sensor is and then go back to this graph and figure out what your liquid level is. You can also hook up to the Ethernet LANs really easily by using a module like this or a shield here like this. This guy's about 10 or 11 bucks. The shield, the official Arduino shield's a lot more expensive, but has room for an SD card, a little bit more capable. So you can connect to your LAN and the internet and send and receive HTTP requests. If you want to put data on a database or look up data that's on the internet, you can do that with one of these. If you want to do wireless communication, you can use something called an XB, and I have one of those right here on this wireless sensor. Little shield, looks kind of like a blue stink bug, but not as bad smelling. Uses 802.15.4 protocol to communicate, and you can build mesh networks. So the cool thing is, these guys can go about 300 or 400 feet line of sight, but if that's not enough for you, you can put a repeater, another XB there, and you can actually start hopping and build a mesh network with up to 10 hops, for example. So you could actually have them go throughout the whole building, just communicating with the next one that it can, and the data will still make it back. Another issue is interfacing with the physical world. So we're dealing here in electronics, you know, very, very small wires, very small voltages. Any given pin on the Arduino can only put out about 40 milliamps, but a lot of times you want to control something bigger, like motors, I guess, one of the bigger things, or relays. So the question is, how do we bridge the gap? And I have an uncle who likes to call these monkey bars for the kids. I never played on them when I was a kid. So for example, one of the things you might want to control is a brushed DC motor. And we all know that these take a lot of current. This one actually comes out of a truck or a bus. It's a windshield wiper motor, and you got a linear servo here and other pretty hefty motors. So if you can only put out 40 or 50 milliamps on a pin, the question is, how do you control, you know, the 10 or 15 amps that you might need to for a motor? And one of the things they've come up with to do this, it's called an H-bridge. So each of these guys here is actually called a MOSFET. And a MOSFET is basically a fancy transistor, and it's a switch that you can turn on and off really, really quickly. Lets a lot of current flow through. It takes a very small signal input. And they're very inexpensive, very easy to come by, very easy to use. So what I'll show you here is, let's say we want to control this as our motor here, and if you all played with motors before, if you hook a voltage one way, the motor spins one way, and if you reverse the battery, it spins the other way. Well, I'll show you how we can do that here and control the speed. So if we turn on Q1 and Q4 at the same time, like that, we get our current flowing through that way, and our motor's going to spin clockwise. And if we turn on Q2 and Q3 at the same time, our current flows the opposite way, and we turn counterclockwise. So we've already got both directions there. And then the way we can control the speed, because a lot of times, having a motor run at full speed is kind of nice, but it's useless for other applications, is what you do is you want to turn on these MOSFETs really, really quickly and turn them off really quickly, and that's called pulse width modulation. So you're turning them on and off hundreds of times a second to control the speed of the motor, because the motor, if you're not giving it full power all the time, it's going to run it somewhere in between 0 and full speed. So further explanation of what PWM is, it's pulse width modulation. And for any given PWM signal, you'll have what's called a duty cycle. And the duty cycle is the percentage of time at any given pulse time that you're up at the top here, up at 5 volts or high. As you can see here, at a 0% duty cycle, you're never at the top. At 25%, you're here a quarter of the time, 50% half time, 75% most of the time. And if you're at 100% duty cycle, you're at 5 volts the whole time. Another important thing about PWM is the frequency, which would be the amount of time in between here. If you're usually better to pulse faster, because then it'll be a little bit smoother. But the issue is sometimes your control system can heat up if you pulse it too fast, because sometimes switching components will have a little bit of hysteresis in them. So if you had a 0% duty cycle, those motors wouldn't be turning at all. They'd be running slowly here, they'd be running a little bit faster here, almost full speed here at 75%, and 100% duty cycle will get you full speed of the motor. So that, in conjunction with an H-bridge circuit, will get you forward, full backward, and any speed in between on a brushed DC motor. And these PWM signals here are just signals, they're electronic signals, very, very low current, almost none at all. So the Arduino can put out the signals necessary to control the MOSFETs to get you what you need. Servo control signals are very, very similar, except you have a pulse width length here. It's not so much a duty cycle as a time. And the time that the pulse width, length of the pulse width corresponds to the position of the servo. So the longer it is, the further turned the servo is. And that's slight difference between a servo control signal and a PWM signal. But a lot of motor controllers actually use servo control signals for brushless DC motors, for example. So that's something else there are libraries in the Arduino to help you with. Typical control systems, one example would be a thermostat. A lot of times your heating system or cooling system in the house is either full on or full off. There is no in between. So you'll set 68 degrees. You'll see maybe it's red, your house is cooling off, and then green, your house is heating up and cooling off and heating up, cooling off, heating up, cooling off. And then someone comes along and says, I want it to be 72, so it heats all the way up to 72. A lot of people like to, when they want to warm it up, turn the thermostat up to 85. That doesn't help at all because the heater can only work so hard, and it can't work any harder no matter how high you turn it up. This is probably acceptable for a house or a building keeping it at a temperature, but if you were doing something like a cruise control system in a car, you'd get sick pretty quickly doing this. So we came up with something a little better, and that's called a PID loop. As you can see, a PID loop produces a lot smoother response to a step change input. For example, if you say your car, sometimes if your car is at like 35 miles an hour and you have the cruise set to 70 and you hit the button saying, I want to accelerate back up again, these are the possibilities it could do depending on how your PID loop is set. And it's called a PID loop because you have a proportional term, an integral term, and a derivative term. And the proportional term takes a look at how far away your actual signal is from where you want to be and compensates based on that. The derivative term will kind of soften the landing. It'll compensate based on how fast you're approaching where you want to be. So if you're approaching where you want to be really fast, it'll slow you down. And the integral term integrates the area under here or here or here. And if you're very, very close to where you want to be but you're not quite there, that'll bring you back down. And these are all gains that can be set depending on how you want the system to behave. We'll go more into that if you take one of my classes. It's too tough to get into it in depth in a short presentation like this and probably would bore everyone to tears. But if you want to see the mathematics, one application for this is like, for example, the thermoelectric modules that you can control. If you can control something, from very low range to very high range or anywhere in between, unlike turning a heating system on and off, but you can do it part way, you could use a PID loop to turn it on part way and keep your temperature maybe at exactly 72 instead of somewhere between 71 and 73. And if you have a vehicle that has one of those electronic, automatic climate control systems and you set it to 72 or 75, this is the type of thing we'd be using there because in a vehicle, you got all this excess from the engine, and so you can control, I want, full heat or I want part heat and part fresh air. So you can be doing full heat into the vehicle all the way down to just a little heat or even air conditioning if you want. So once again, anyone ever seen anybody with these automatic climate control systems in their vehicle and it's 20 degrees out in the winter and they turn the thing up to 85 degrees? It's not doing them any good because if it's 20 degrees inside the car and it's set to 85 in the climate control system, the car already knows that you want it warmer and it's very, very far away from the temperature that you'd like. So even if you just leave the thing at 72 degrees, which is where you want it to be, it'll heat up just as quickly. Another thing that's very important when you're dealing with robotics, just like really any field, plumbing, being an electrician, or even in the medical field, is having the right hardware. It makes your life a lot easier to have, good soldering iron, the right wires, multimeters, power supplies, screwdrivers, any kinds of tools, just like being an auto mechanic. It's very, very frustrating, and that's often the one thing you need if you're trying to hook things together is all this stuff. And if you have access to all this, it makes your projects go much more smoothly. Otherwise, you're sitting around trying to order all the time. And one of the nice things about having the FabLab here is that all this stuff is available downstairs We just got a lot of it in, but it's going to make projects a lot easier if you don't have all this, you know, in your basement or something already. So some of the things that Arduino is great for, prototyping, because now it's very cheap and easy to get into it. You can build something very rapidly, very cost effectively. There's a lot of help available. Experimentation, likewise. Data logging, because you can do it cheaply. Low volume production. People often ask, is Arduino actually used out in the field? In production items, yes, it's actually used in the ampule sealer. And that's a very, you know, high dollar item out there. We haven't had any issues at all with the microprocessor. I have no reason to believe that microprocessor is any less reliable than any other particular microprocessor out there as long as you meet the operating conditions on the data sheet. You can replace PLCs, and you could do wireless communication and internet, which was, you know, a lot tougher back in the day. So some of the cool projects I found that people have done, this is someone was trying to replicate a Nest, or I guess maybe this was possibly a precursor to the Nest. You have an Arduino here, the servo controlling a thermostat, and a temperature sensor here. Someone else built a sump pump monitor to see how often their sump pump was running, and they got a logger file here, and you can see their SD card, so they could take that, put it in their computer, and you know, tell if that was overactive. It's a lot of wiring there they got for it. And I thought this was really cool, so I figured I'd put this up here. Someone was actually replacing a readout on the speedometer for a Ford Mustang. Now, I don't know if they were doing this to enhance the capabilities or because the original one died, and I'm not here to make any comment on the reliability or lack thereof of, you know, any brand of vehicles. But ironically, shortly after I put this in, I got a call from an aircraft company in Oregon that wanted me to do something similar for their aircraft because they couldn't put the readouts in the glass panels quickly enough to deliver their aircraft. So I'm actually working on something similar to this for something that's going to go up in the air, which is really cool. I don't know that this is an Arduino, but it's a beer tossing fridge. So I figured that was cool to put in there. This is a kit. I actually built something very similar. This is one of the first things I built. These are infrared sensors here, and these are the sensors, and these are infrared lights. Each wheel here is individually controlled. So what you can do is you can program this so if it's moving toward a wall and this guy senses a wall, you speed up the wheel here, slow down this one, and have it turn away from the wall so it's not hitting anything, kind of like the Roomba robots or the Scuba robots. You can participate in competitions like robotics soccer, either completely autonomous or remote controlled. You can have a device like this to grab things and pick them up and move them somewhere else. If you know, things are too organized and you need to clutter them, you can have it move things around randomly, or get little kids. You can build a Mars rover, which is really cool. So that's a robotic application. You can build a drone. A lot of times drones, there are kits that you can buy that have all the gyroscopes and programming you need in them, and they're very, very easy to fly. Or you can build your own. There's actually a company out there called eVolo that's building a life-size gyrocopter with 18 of these blades on them so that there's some redundancy failover. There's a video on YouTube. I probably should have put it in there, but people are working on actually putting people in these. And the only way to make a drone more awesome is to make it bigger and put missiles on it. So for use in the military, another application in robotics. And then Carnegie Mellon has a Mobot competition. So when you're on the tour of Carnegie Mellon or just walking around, you see a sidewalk and you see all these white lines here, and you're wondering, why on earth would someone put white lines on the sidewalk? You know, can't the people at Carnegie Mellon follow the sidewalk, or they really need the white line there to guide them? And it turns out that they have a competition every year at the big event called Carnival in April, which is coming up in a few months if anyone wants to make a trek out to Pittsburgh. And what it is a competition where robots are actually following these lines down to the finish line. This is one of the cars that was used. I picked this picture because it has an Arduino in it and an LCD screen, and I guess that's an interface board of one form or another. But there are a variety of ways to sense the lines. You can use sensors that sense the reflectance of the lines, or you can use cameras, for example, with image processing to get down there to the end of the field as quickly as possible. Here's someone setting up their robot. Two more people. I don't know why they painted theirs pink or if they're standing in front of someone else's. But as you can see, it's a very popular event. A lot of people around taking pictures, probably because there's food there. But the other thing is down at the bottom it gets a little more complicated because you see they had extra lines there and there's certain gates you got to go through. So you can program which gates you got to go through. But the car has to make a couple of decisions and the goal is not hit the flags. One other important part of Carnival is called Buggy. And basically a lot of sororities, fraternities, or other groups participate in this. And the goal is to get the biggest, fastest person you can here pushing this thing and the smallest, lightest person you can inside here steering the thing. So yes, there actually is someone inside there. And they do this every year. They got a course all marked out, and they have a support truck riding around behind it to help with timing and make sure everyone's okay. So I was walking around last year at Carnegie Mellon and ran into this, and this is called Robo Buggy. So they're making a buggy there, but they decided it'd be cool to try to eliminate the person inside it, and they actually have an Arduino Mega board in there that they're trying to use to steer the thing. But I guess someone still has to push it because that would be unfair to have it, automatically powered with a battery. But that's another example of robotics, going on at Carnegie Mellon. Carnegie Mellon also won the DARPA competition a few years ago. They have quite a few sponsors here, but they had, some of the challenges out in the desert and the urban vehicle challenge. So this is basically the precursor to the self-driving car with a heck of a lot of sensors on it. Carnegie Mellon also has a roboceptionist. So instead of hiring someone to sit there and answer all your questions, they got this thing with a creepy-looking face here that you can ask questions to or type to, and it'll tell you what it thinks you want to know. And you can make either a clone of yourself as a robot or a companion robot, depending on what your desire is and what you want to program it to do. I don't know if there's anything more that needs to be said about that. I mean, it looks pretty lifelike. I'm not really sure what it does, except for smiles at you when you poke it. So the question is, how can you get involved? And one of the best ways to get involved is, honestly, to just buy one and start experimenting. And the Arduino, the Uno itself costs $25. So if you're short on ideas for like a 6-year-old or a cousin or your son or something or daughter or whatnot, it makes a great birthday or winter holiday gift. Personally, you want to find a project to work on because when you're doing something, you're self-motivated. You're more apt to try to get things done and learn about them. So if you find a project to work on, that can help you get involved. Or participate in a competition like the Mobot competition. There are also lines on just about every road here if you don't mind dodging cars, but I'd probably recommend against that. Or you could take Arduino classes. So a brief overview of some of the classes that the FabLab offers. They offer Introduction to Arduino. So it's basically building a digital clock and electronic basics. Then they have level 2, which is building a project of your choice, and then learning more about the components you want to use and advanced techniques. Building an eggbot. And I'm teaching Robotics Smart Car, which is more about speccing and interfacing with sensors and other common electrical components. So a lot of times you need to figure out, well, which resistors do I want to buy? Which relays do I want to buy? How do I use them? How do I make the LEDs do what I want them to do? And then the Ultimate Smart Car is the next level of that, where you're learning advanced Arduino topics about how to use classes and include files and more functions, managing your processor resources appropriately, wireless communication, and internet connectivity. Does anyone have any questions? What if you don't want to learn? Well, what do you know already? Well, it's going to be kind of hard. You'll have to either pair up with someone who knows C++ or you're not going to be able to program. Yes, there are. They're not as popular, though. I mean, you can use, like, for example, Raspberry Pi. Raspberry Pi is a whole different level. It's, Linux-based, probably a lot more complicated. The Arduino is more into the digital I/Os and interfacing with sensors versus being a whole computer. But a lot of the microprocessors use very similar programming techniques and languages. And to be honest, you really only need to learn, very, very low level of it to actually be successful making things happen. And there are a lot of tutorials out there.
Are there other places to buy things like motors and stuff like
You can buy any motor out there from anywhere. So I use a variety of online places myself, and as I said, that one motor is off of a truck or a bus for windshield wipers, and I'm running that with an Arduino, and that wasn't in their wildest dreams when they started putting it on the trucks for windshield wipers. So yeah, you can run, you could launch a space shuttle with this if you hooked it up correctly. Or land a lunar rover. Jeff, do you have anything to add?
Any other questions?
No, I just came in to see how things are going.
Okay.
Any other questions? All right. Well then.
Okay. I could show you a live demo of a couple of things. So you can clap. Okay. Promised you the demonstration. This is actually live data coming from that building with the Bethlehem Municipal Water Authority. It's actually located on the intersection of Catasauqua and Pennsylvania Avenues, not too terribly far from here. And it's updating every 30 seconds. So on the East Main Line here and the South Main Line, we're measuring millions of gallons a day in flow. And on the south pressure, high pressure, and east pressure line, we're measuring the pounds per square inch in the line. Now we're using the standard 4 to 20 milliamp current sensors that are out there in the field because they're already out there, and we want to use the best sensors available. And we're not necessarily trying to replace the sensors because they have sensors in place, but those sensors will put out a current we can measure that we can correlate to the actual values that they're getting. And the thing is, these lines should be pretty consistent because they're not supposed to be changing that much. A couple other things I can show you here. You can pass this around if you want. So what that is a very low power ultrasonic sensor that I built for someone, the guy in Boston actually, for measuring chemical tank levels. And that would actually go into this here. So this is the case for that. You'd screw this into the top of the tank. You'd have that in it, and the ultrasonic sensor would send a ping down and hear the echo back, and you'd be able to tell how much liquid was in the tank. And the reason he wanted me to help him was because oftentimes he was filling a lot of tanks in one area. Each customer would have 3 to 5 tanks, and the device that he was using, everyone had a cellular unit, so he was paying communication on every single unit. But if you have several in the same area, that's got an XB on it, one of those wireless devices, and you can go to a base station like that red box there and aggregate that all through either one cradle point, one cellular internet connection, or even straight Ethernet out the building if you have a cable or DSL modem or some other internet connection, and you're saving all that communication cost. So that's designed to take a reading every 2 hours and last 2 to 3 years on a pack of 3 AA batteries. So that's one of the sensors that I brought. We can actually activate that. This here is the E-tape that I showed you. And then this here is another ultrasonic sensor. This is just an anema box, and this is weatherproof, so this will hold up better outdoors instead of inside a chemical tank. But this is a much more expensive sensor than that one, so I bought fewer of them. But what happens with the ultrasonic sensor that's being passed around is that data goes into this base station here, over the XB, and then that base station connects via Ethernet to this cradle point up here. And that cradle point is on Verizon cellular network, so that has internet access. So anytime that gets data, that data gets sent to a database, and then it's online, and then you can put it into something like this or run reports off of it. So I can show you the latest data that is coming off of that. All right, and we haven't got an update in a while. But as you can see, this is the data that the sensor in the Water Authority place is giving us. It's giving us current readings for a couple of things that we're measuring. We're not measuring any analogs or digitals, but if we hook up that sensor there, we can get an ultrasonic range reading. So if you want a quick demo here. Yep. Here, you want to power this up? Here, we're going to aim this at the floor. Going to give it battery power here. Okay. Let's start passing it around. It takes about 8 seconds to transmit the reading of the base station, and the base station is going to transmit to the cradle point. And then that should show up here very shortly. Might have to do it 2 or 3 times, but just leave the battery in. You try popping the battery off and on again, Derek? All right, thanks. And aiming it at something while you're doing it? All right. Well, or just unplug the connector. Okay, all right. There we go. Okay, we got our reading now, 31 seconds ago. So it measured when I held it above the floor, 111 centimeters. So that's our ultrasonic range there. So that's how the data is getting into the database. Anyone have any other questions? Anyone excited? Okay. Yes. No, the fluid doesn't have to be conductive. You can put it in water. They actually say you can put it in like a powder, because what happens is the pressure of the fluid pushes against it, and that changes the resistance. So I could put it in that pitcher of water back there, and it would measure it.
Do they make those longer than a foot?
Yes, they custom print these, so you can get them basically as long as you want. I mean, as long as they can make them, but they can make them at least a couple of feet.
Any more questions? All right. Thank you, Brian.
All right, you're welcome.
And we'll just reiterate, if you're interested in this stuff, you need to grab one of the green books in the back. And anybody who didn't get to see the Fab Lab beforehand, make sure you go down and check out the Fab Lab. James will be giving a tour. Grab the green books, look at page 38, and make sure you sign up for the robotics stuff. Either one of the weeknight classes or the weekend classes. Jeff, do you want to say a bit about the classes quick before we close? We'll have an open mic just as soon as Jeff's done.
I wasn't here for the presentation, but I've heard Brian give so many fantastic presentations. We've called on him so many times to dig us out of certain jams with our electronics, especially that I teach the guitar classes. And there's always some crazy stuff that we want to do in the guitars, and it's, hey, Brian, how do we do this? So thank you very much, Brian. You're just a great asset. I'm real excited about these robotics classes. I think it's time really to take the lead as a Fab Lab, and I think, I'm not exaggerating, we have one of the best Fab Labs in the country. No question about it. And I think it's time for us to really take the lead and start to do some very high-tech stuff, come up with some original designs, both electronic, from an artistic standpoint, from a design standpoint. We have 20 instructors. We have a lot of courses, but we also have a lot of people who are just aching to create something. So anyone of you who want to be involved in coming in and helping out with a project like that, you're welcome to. So we just started an initiative now to try to make something in robotics, of course, because that's the buzz. And the robotics classes that we're giving are going to be a lot of fun. We're hoping to do it in the competition. Saturday is from 8 o'clock in the morning all the way till whenever. And then we also have these traditional classes, which are 3 hours a week, giving you time to come in between and work during the open labs. All of you can come down and sign on to the email list. Every Friday I'll give you an email which tells you when our open labs are. Of course, you can always find out when the courses are just by going online. But you can come in from 9 to 4 in the morning or 9 to 4 in the day. We're always open. But we do have off times, like in the evening on Saturdays when there's no classes going on, where we would be open for you to come in and work on whatever you want to work on. So the lab is just a community place. There's no intimidation. It's an easy access to technology, and all of us are trying to raise the process level to the highest possible technology that we can, not leaving out, of course, traditional skills and manufacturing techniques. That, to me, is extremely important. They go together. And a lot of fab labs don't really pay too much attention to that. So thank you very much for coming. Please come down to the Fab Lab and take a tour. James gives the best tour I've ever gone on. That's not an understatement.
All right, yeah, don't miss James' tour. Thank you for coming out to the meetup this evening, and again, thanks the Fab Lab for hosting us tonight. And we will have an open mic. If you guys, anybody have any, line up right by me, 1 minute. Anybody, any announcements? If not, I will announce again where you go to meetup.com to see the rest.